I think most of you all know me, Mark Cichy. I've probably taught most of you, if not all of you, at one point or another in 113. I'm here to talk about one of our projects, actually, that our office is working on right now, which is the retrofit to Lansdowne Stadium in Ottawa. And so what I'm going to do is I'm basically divided the presentation into, I'd say, about four major components. One is basically just the program of the project. The second is sort of the details and honoring of the original design. Then the detailing for manufacturing, and then also tooling and kind of designing for manufacturing and fabrication. So thinking a little bit differently about how we build buildings. Traditionally, when we're thinking of things as architects, we're actually thinking about what the design or the concept is. More so today, I'm going to be basically talking about, that not being really our scope, but our scope is kind of realizing that or interpreting that in the realization of the manufacturing of the thing. So basically, what I want to do quickly is position our office in relationship to all of these other consultants, which are part of basically what you would consider a conventional structure of contract administration, which is to say that at the top of the food chain, obviously, you have the client, right? So the client comes to the architect and says, hey, we've got some money set aside. We want you guys to, either give us, do a competition whereby a number of design firms compete for the job, or they go directly, in this case, to the architect and say, you know what, we've got this job. We'd like you guys to put forth your best effort and give us some concepts for how we can, approach this thing. And so then you have, obviously, involved in that process is your structural engineer. And now I'm excluding things like mechanical engineering, electrical engineering, lighting, consulting, and stuff like that at this point, because what we're primarily dealing with right now, specifically on this project, is there are elements of interface between electrical and mechanical and whatnot, but primarily what it is it's the veil component. And so we're primarily dealing with the architect and the structural engineer for coordination. And so basically what happens is all of these people then tender the job to a general contractor. The general contractor obviously decides what is in their scope to cover. So in this case, obviously, when you're dealing with complex geometries like we are in this case and many other projects, what happens is that ends up going, subcontracted out to someone who actually specializes and understands these sorts of things. So you've got a fabricator who does this sort of thing all the time, deals with nonlinear geometry, and so they've got a history of delivering on projects like this. So the GC is not even going to get involved there. They're just going to say, you know what, this is what you guys do for a living. You should just take care of it, manage it, and get it done. And so that's where we come in. Essentially what our office does is kind of all of these things here, but on that component, which is, what some are considering to kind of farm out to the expert. And so what our job is essentially to rationalize the architect's design, work with the base building structural engineer who's already done their pre-analysis, and kind of go through each and every single detail and the geometry supplied to us, work that out, deal with the schedule, deal with coordination with the GC to make sure that the concrete is being poured in the right place for where we need our base plates, and to then generate all of that and manage that and coordinate with all these different people so that the thing can actually be erected, right? So we'll actually work with the erector or the fabricator themselves, and actually our client is normally the fabricator. So the fabricator, the guy who builds or erects the thing, will just say, look, we understand you guys know your way around paperwork, you know your way around drawings, you've got experience in these things going up, and it's an asset that you do this non-linearly, meaning that you're doing this with abstract forms and you're not resolving just rectangles, because otherwise we wouldn't need you. So that's why we come into play. And so we change the model a little bit, because what it means is that traditionally what happens is someone in our position who would be considered a subcontractor would actually have to go through the GC to get to the architect and the engineer in order to communicate, right? Which is Actually, on the job I'm showing you, ironically, is the architect is pushing for that model as much as possible. But the reality is, in order to meet the timelines and react to kind of the delivery in which these things need to be sped up, we've got to perform a serious amount of direct communication with all these guys to get the thing built. So, the team, as you can see right here, there's a building design team, obviously, which is the base building. And that's composed of Parmerlo, which is a general contractor, Cannon Design, whom I'm sure maybe some of you even worked for or definitely have heard of, and then there's Halsall Associates, their office here in Toronto on Yonge Street. So our Vail team is basically us, another structural engineer, which is Moses Structures. I'm not sure if any of you ever heard of them, but you can Google them and you'll see. Spring Valley Custom Corp, which is essentially the fabricator, and then Structurelam, which is actually a company out of British Columbia who works primarily with Glulam members. So you'll see when I show you in a number of slides coming that they've got quite a sophisticated facility out there. And actually a few weeks ago I was out in Penticton, which is where their primary manufacturing facility is, and so I brought some photos and some video from that. So this is the architect's intent, essentially, for the conceptual design. You know, the fact that the stadium is a porous entity, and so you can actually, I guess, allow that kind of transgression to bleed through one side of this building to the other. Now, this all sounds great conceptually. In reality, there's a big block of concrete between the field and the exterior in which you see it from the road, so I'm not sure how porous it really is, but conceptually it's a beautiful idea. So this is the program. So the program is that they're retrofitting an aging stadium, which is basically crumbling into ashes, right? It's currently, what are they saying? It's seating 24,000, and they're looking to basically double the amount of seating so that they can host international events, right? Things like World Cup soccer events and things like that, football games, maybe host an NFL game or something like that. So in order to kind of reclaim some of that glory, they've got to obviously perform some major renovations. And so, you know, this is just a small fraction of an overall master plan that's actually being dealt with the city. So you can see that basically our component is the south stands here, right? So we're working on a very discrete, dedicated component to all of this, you know, entire block here. They're doing a little bit more than just doing the South Vail, but our focus is the South Vail because we specialize in very unique construction methodologies and erection. So here are some images actually from the architect that basically show what we're working on, which is this wood structure here. So this is what they're referring to when they're saying porous, right? Essentially, what it is a series of primary and secondary wood frame members. The entire thing is composed of glulam members. So this is actually looking from the north to the south, and you can see the stands here, and the field is down here on the ground plane here on the other side of the hill. But this whole thing basically arches over from one side of the site into the center of the stadium. There you go. So this is actually not a very good perspective, because in reality what happens is the curve is actually, first of all, a little bit off, as you'll see when I show you some drawings and some details. But what happens is the Vail edge actually comes out further over here. This is kind of an earlier image that they've got. And so this is kind of the feeling between the interstitial space, between the exterior, which we saw from that view from the river, from the Ottawa River, and the back face of the stands, which is the seating area. So what you're looking at is basically concrete to the left here, and then the Vail on the right. And it's actually, again, this view is kind of a little bit off because we actually have a ground plane over here on the right. So to see a tree that high up is really not a realistic portrayal of what's going on. So, okay, step one is essentially understanding the architect's intent, right? So we already discovered what the architect's intent was to establish this kind of porous relationship between different spaces of the building, or at the very least the primary component, which is the Vail. And so there's that to kind of rationalize those curves, right? We need to understand what the geometry is, what it means, and really what is achievable, right? Because, I mean, you could you could drop spaghetti on something. It doesn't mean that you can actually go ahead and rationalize it to make it physically possible. So we need to understand where those limitations are. But above and beyond that, we need to be able to do that for 40% less money. So this is the challenge, is that originally the project was supposed to cost $7 million to fabricate just that wood veil, okay? And all of the associated steel elements as well, right? And then they came to us and they said, well, you know what, we're going to have to put the project on hold because we really don't have $7 million. So you have to find a way to make it $4 million and give us everything we want. Which, you know, you're thinking, well, okay, that's fine. So where can we cut back? Well, when you look at these sections, these large arcs here are referred to as primary members, okay? So they're the main kind of spinal elements of this structure, which actually span a complete distance and plan of about 150 meters. And they're about, at the top here, at the crest here, they're about, I guess, 38 meters tall. So you're looking at a piece of wood that's basically arching and curving out over the stands from the ground with basically the only support, lateral support at the top anyways here, is what we refer to as trees, okay? So this thing is very tensile, very light. And essentially, you know, we had to figure out, okay, where can we save $3 million is basically the short of it. Well, as you can see here, if we look at the section of these things kind of closely, you can see, if you look at this one actually is a good example, you can see there's kind of like a little bump right here on the backside. It's like a little hump or a wart almost, right? And so these are a product of, and I'll say, like, my education is from this school, right? So we're educated to be architects. So, you know, when we are given things like Rhino and Grasshopper and we're like, wow, cool guys, we can play with this like putty, this is awesome, right? You're not really rationalizing anything other than your concept, and you're not, I mean, the rationalization, the level you go to is, does it meet my minimum criteria for what the conceptual theory is for the project, right? So you're not really thinking, you know, what does that little bump mean, you know, when we get into construction? You're just like, okay, it's there. Someone's going to tell me what the cost of that bump is, which is essentially, sadly to say, quite high. So what you have to do is understand, okay, you know, we have these little bumps here, and we call these little things here eyes, which are basically openings in the veil above grade, which allow people to see out completely unobstructed at certain windows, right, that they've captured, to presumably frame certain viewpoints. So, you know, where can we save money? Okay, well, if we look really closely, you guys can see these little black things here that they almost look like tons of tiny little hairs. If you look really closely, I mean, unfortunately the drawing is actually scaled quite small, but these are spaced right now I'm saying, is in the architect's original design, they're spaced at around 200 millimeters, which is like 8 inches. That's a hell of a lot of wood, right? So right there, we can look at that and we can say, okay, there's number one, there's a huge potential for cost savings there, but, you know, as the architect, you know, we take stuff out of there, the architect's going to say, no friggin' way, right? So how can we do this and still keep it within reason? Second thing is that these members right now have not been optimized whatsoever. It's, let's just put in a big chunky size of wood and whatever it needs to be, it needs to be. Well, you know, the arc length of this thing is like 200 feet, right? Which is huge. So what if we cut it and we optimize the sizing based on different types of lamination? So there's a series of discussions here in which, as I move through, what you'll see here is basically our rationalizing. So we've now performed a rationalization on these curves in which we've taken into account certain factors, let's say, that basically drive a number of things. So first of all, the length of the thing needs to be shippable. It's coming from British Columbia. You can't stick something that's 200 feet on like 3 trucks, drive one backwards and one forwards, and, you know, ship something that large. So that's number one. Number two is, can we satisfy a radius like this? Like physically, can it be constructed, a radius that is, that tight? Can we build that? And the answer is yes, kind of, sort of, but we have to obey certain restrictions. And then kind of the third thing is, can we optimize, since these are laminations, meaning there are several pieces of wood that are glued together to form ultimately the section size that we require structurally in order to sustain the load, how can we optimize that? So this drawing essentially answers all three of those questions. And there are several more. I mean, like I said, there are 24 of these V's, right? So there are 24 primary sections. But what you're looking at here is this line indicates where there's a splice location, okay? So it indicates where the continuous member is cut in order to maximize and reduce the cost of shipping and making of the thing, right? Because we have limitations on certain radii that we can have. They physically cannot bend or laminate wood beyond a certain thickness at a certain radius. And most of the time, it depends on what the lamination is. So if you're using pieces of wood to basically glue together and then curve, as we'll see in a minute when I show you a photo of what that looks like in a jig, we have basically two primary options. One is we can use a 19 millimeter lam, which is basically 3/4 of an inch, right, standard board, or we could use a 1.5 inch, which is essentially like a 2x6, 2x8, right, is basically 1.5 inches roughly. So we have those two options. If we need to do anything less than that to achieve a tighter radius, it's possible. But what happens is we're just taking a 3/4 inch board and we're planing the hell out of it until we get it to the size we need in order to achieve the radius. So this did not take that into account. And so they had radiuses here that, hell yeah, we could have built that. But we would have had to use like 10 millimeter laminations, which is equivalent to like basically throwing away 3 boards for every 1 board we're using, right? So, okay, now we understand that. So how does that affect the main curvature? Well, really, in reality, the maximum we're out in some of these relative to the original design is by 6 millimeters, okay? 6 millimeters on something that large is inconsequential. Like you cannot even see it. So now we've got one other caveat or limitation to all this, which is to say that if we look closely at this arc here, you can see that this is kind of a gentle slope, right? Over here we can see that we've got at one of the eyes, we have quite a tight curvature here going both directions. So the one last caveat is that at situations like this, we have a certain limit to how much extra tangent we need at a curve, which basically means where this curve curves back, we need a certain amount of extra material so that the wood, once glued and then released, doesn't just split itself right apart at the seam. Because we're laminating pieces of wood together, if we don't have enough tangent left on the arc, they basically will rip themselves apart once they're released out of the jig. So you talk to, okay, so here's a good example where we're actually zooming in here. So you can see here all of these radii are indicated on here. And what matters, and what's kind of funny about this is that we did this whole exercise and it took a considerable amount of time. I mean, these drawings are like ridiculously simplified, but to engineers, they look at these and it's like an engineer's wet dream. It's just everything is there. It's completely obvious as to what it is they need to know right away, and that's it. They love this. So we originally did this whole thing, and we did it based on the center line of the member, because the engineer kept saying, we need to know the center lines, we need the center lines, we need the center lines, we need to run our analysis. So then we started talking to StructureLam, and StructureLam said, well, why the hell have you guys done all of this based on center lines? And we said, well, because the engineer said that the center line governs all of their calculations. They can't calculate their loads unless they do everything based on the center line. And they said, well, that means nothing to us because all of our limitations are based on the inside radius. So we sat there and we thought, great. Now we've got to go ahead and perform this analysis all over again And what do you want to bet we're going to be out, and we're going to have to completely change things here? Well, we were pretty damn lucky because everything was built parametrically. So basically all we had to do was basically move the line, establish the new radius, and then modify the parameter that defined the curve, and then we could basically do a subtraction. So originally we were 6 mil out. Once we added the extra tangent information and the inside curve radius as opposed to the center line, we were an extra 3 mil out. So effectively we were 9 mil out, which is what, 3/8, I guess, of an inch roughly. Like 10 mil, I think, is 3/8. So still, again, at that scale, we're pretty darn close. But you can see here that this little bit here is a 12 mil lamination, so we're throwing away a lot of material, but the architect must have this member. It's like absolutely crucial. They will not throw it away. And then you can see here the overall arc length of this thing is actually, I was exaggerating a little bit, but it's about 70 feet from this tip here down to the bottom, right? But we've got, I mean, the only straight member here is from the base to about here, and then every other piece of this is curved. So the structural analysis is a little bit difficult to basically achieve because we've got to work with inverse curves and whatnot. So here this illustrates basically, let me just talk a little bit about the language. So one of these guys here, one of these deep guys is called a primary. One of these here, which is basically like a wood screen or slat, is referred to as a secondary. And these guys here, which are horizontal, are referred to as props, okay? And what we have here is basically a base plate that's cast in concrete. And we'll see what the detail is for this later on, and you'll see that there's a bit of play in the kind of design structurally of this thing being like a pin connection as opposed to a rigid connection, which would basically just rip the plate out of the concrete because of all of the, I mean, wood is a live material, right? And it has memory. So even after they dry these things, the glue dries, they plane them off, they put them in place. Forever, they're going to be changing when they get hot and cold. They're going to be bending, twisting, expanding, contracting. So really, almost every single joint or connection to these things needs to have mobility and flexibility. Okay, so what you can see here is, if you guys could see kind of, there's a bit of a gray member here and here that's sticking out beyond the wood color. And basically what that's indicating is the original design or concept of the architect relative to what we need to do in order to achieve constructability. Excuse me. And so what we had to do was, and this is actually a good point here, why I took this image was, if you recall, what I was talking about was, you know, rationalizing things and optimization, right? Well, what this shows is that we've actually taken out every other member here, and we've actually reduced the count on the top of the veil by half. So we reduced all of these little secondaries here. We had originally 2,470 something of them, but we reduced that to 1,783. So we cut like 600 of the, like a serious amount of material right away out of the budget, which amounted to roughly, I don't know, I think it was like a couple of $1 million. So boom, right away, you know, we're talking about cutting 4, we've just got half of it by doing that, right? And so, you know, what you're seeing here again is the original, right, curve. Now, remember, when I'm saying that we're out by like 9 or 10 mil, what I mean is on the inside face, we're out by 9 or 10 mil. Not on the top face, because that's obviously more than 9 or 10 mil, right? But no one's ever going to see that anyways. So it doesn't matter. So essentially, these are our trees right here. What I'm showing you right now is that these trees have a base plate assembly that sits on top of the concrete and basically supporting the underside of these thickenings here that happen on the underside of the wood members. And then every so often you have what we refer to as a deep purlin, which is essentially creating lateral rigidity between each bay of members. And then we're actually, I mean, very crudely, but we're doing it, is that we're modeling in the speakers and the lighting because there was an element of obsession, rather, with the locations of these relative to the veil edge. Because The architect was saying, well, you know, these are supposed to be either at the edge or within 500 millimeters set back. And the structural engineer is saying, well, you know, we've just cut a meter off the end so that we could reduce the loading and therefore, you know, not have to thicken the member, right, because it looks hideous. And therefore, we can move these further back, which means that we can now optimize everything further. And the architect comes in and says, no, we're going to leave them at the front edge. And the structural engineer says, well, then why did we just cut the thing back? Like, there's no point to this. If we're optimizing and then just putting something in place of what we were optimizing, what's the point of optimizing it at all? So essentially, there was a circular discussion about, you know, how can we maintain the sense of optimization? Because that was the point to do it in the beginning, was to save money. And so ultimately what happened was everyone was, you know, kind of in agreement that yes, the best thing was to indeed move it back. So you talk to a structural engineer, that's what you get. When we're talking about optimizing curves, what do? They fax us a sheet of, okay, these are the tables. And we look at it and we're like, that's great. If I went to structural engineering, like if I went to Waterloo for structural engineering and I knew what the loading tables even meant, then this would really help me. But when you look at it a little bit more closely, they start to talk about things like, you know, minimum radii of the members, how long, exactly the things I was talking about before. And so, you know, you can read it and the CSA standard kind of makes sense, but not to the extent that you really would need to know. So what I found more useful was this. When I sat there and the guy actually took me to the plant floor, and you can see all this brown goopy stuff is basically glue, and said, this is why that table is irrelevant and irrelevant at the same time. Because the table will tell you, yes, this is achievable, but in reality, no, it's not, because of the tangent arc issue. So we were going based on engineering data, which theoretically works fine, but the reality when you're talking about construction or fabrication or manufacturing is that depending on the material and species of wood, those tables kind of don't really satisfy the problem. And the issue was that, of course, what was being specified here is a yellow cedar, which can only be found in a discrete area in British Columbia in a remote location, which is very difficult to log, that only 2 logging companies actually supply wood for or material for. So what we're looking at right here is essentially, and this is why I said before, this is actually really interesting because it actually talks about how these things are made. And what's really funny about all of this is that we're standing on our heads on one arm and then juggling 3 balls and holding a cup with our feet with digital software to figure all of this crazy stuff out. And really, it comes down to guys pulling wood against a piece of steel and then tightening a bolt to make it sit there with a bunch of glue in between, right? So it's kind of like you're sitting there and you think to yourself, wow, this is crazy. I mean, we're doing all of this work, and really, at the end of the day, I mean, you know, the biggest determining factor is having the experience and the know-how of what the reaction of the physical material is, really. I mean, it's really interesting. And so what you're finding here is that every single time these guys need to develop an arc, whether it's for this project, whether it's for another project, they have to basically take these jigs, bolt them to the concrete floor in a different configuration every single time. So they will have to do this 24 times just for this project. Actually, no, I lied, actually, because we have a splice. So we have 2 pieces for every 24 bays. So they will have to do it 48 times. They will have to re-bolt these things in a different configuration every single time and let them sit. So you can imagine when you're talking about timelines now, you know, before we're even talking about manufacturing time, CNCing, machine time, people time, design time, anything, you know, there are all these factors that affect scheduling, right? And you start to realize how specified and specific all of this really is. Everything is a one-off, right? And never mind before we get into machining out pockets and holes inside of a solid piece of material that somehow you have to get in from the outside without ever showing that you were in there. right? So we'll talk about that. So essentially, what I have here is an overview of elements. And so what I'm going to be doing here in the next few slides is I'm going to actually focus on one bay, because to go through all of this basically all the time, the scale is just too large, so it's difficult to actually focus on discrete components. So we're going to focus on, I think it's 1, 2, 3, 4. So this bay right here, bay 5, which has a door opening at the base and arcs over. Now, basically, this is just showing you all of the different arches. So you're seeing B24, 23, 22 all the way across, and then we have some purlins going across here. So, so for the architect to model this is actually really easy because, well, okay, I'm going to say it's easy from my perspective, because basically all they do is they open up Rhino, in Grasshopper, they say, okay, we want extrusion along here, we want to control it with our little rig, and just blah, 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 and then boom, it just happens, right? Yay for parametric design, awesome. Score one off. So, but when it comes time to manufacturing it, what that does is that, and we'll get into geometry and things like that in a moment, but when you loft an object, it actually stays perpendicular to the rail in which it's lofted on, which means that it actually bends. Well, wood doesn't really bend when you're using a straight member, right? It's an extruded object. It's not, or rather, sorry, it's not an extruded object. It comes out in a board form, right? So it's not actually twisting, which is basically means that every 1,783 of these things has to be modeled by hand by a person, which means that this, well, I can tell you right now, it took a month to get 2 guys to basically model every single one of these damn purlins. So it's quite a challenge, right? Again, it's just emphasizing the fact that all of these things are essentially unique and have a different cut. And this is before we even say, we've had the talk with the architect where we say, the detail we have right here, because we want to basically appear as though there's a sense of continuity across the whole veil, right? So the exterior skin or cladding of this thing, which is all of these purlins, has to appear as though it's one continuous line. That's the point, right? And so in order to achieve that, when these things saddle over a primary, is to create a notch in the section of the wood. Well, we've got 1,783 of these things. Every single one is at a different angle. That means that every single one has to be CNC'd individually and have a program run on it, which is okay, fine, if we could do that, but some guy's got to stand there and put the piece of wood in the machine, put the next piece of wood in the machine 1,783 times. Well, okay, that's fine, but that same machine needs to be used for the primaries at the same time. So, you start to pile up all these things. Yeah, we can machine anything, but the fact of the matter is these machines are expensive. They cost money. They're like $5 million each. You can't own 17 of them in one facility, no matter how rich you are. So you've got to rationalize that even further and optimize that. So, there needs, we need to design rather a detail that satisfies the continuity of what the architectural form is, but still will honor the constructability of the thing. So basically what this diagram is just showing us is our modified spacing, right? So in some cases, that 200 mil inside face to inside face became, I believe that's 654 or something like that. So in some cases, almost 3 times as much, but that is the result of cutting away $4 million of fat, right? It's just, yeah, you gotta pick your battles, right? So what we've got here is essentially an ISO or AXO, I guess you could say, of the end of the, well, if we just go back here, it's this little tail end here. And so what we're looking at here is our drawings start at a very kind of zoomed out level where we look at everything encompassing every object within here. But our drawings have to include down to the level of the last little bolt that goes through a piece of steel that actually holds 2 plates together. We don't, we're not doing typical details, we're doing atypical everything. So our shop drawings need to essentially include every single element. So what you're seeing here is that, we refer to things as assemblies and parts, right? Not really so much as just encompassing objects. And so what you're seeing here is basically a bunch of different assemblies, and as I was saying here, these are the props, horizontal props that support the primaries, right? Here's a splice with a HSS tie-in across for lateral support. And then we've got basically these tree elements that support the thing from underneath so that it doesn't fall over. And over here on the right, what we've got here is a takeoff, which is dynamically driven by this geometry. So all of the data for our arc lengths and our lines, which are also parametric, right, are driving these Excel tables, which then are linked into a document that we've created letterhead and everything for. So when we, modify this, it's one way. I'll be honest here. It's one way from geometry to the spreadsheet. You don't modify the spreadsheet and then go back to the geometry. For a number of reasons. It would be catastrophic. So, what this is showing is what our purlin size is. So it's an 80 by 246, right? And what number it is. So this is actually the bay, and then we've registered that, this first line item here is actually at the base here. So there's an intense amount of coordination and documentation that needs to happen. We're talking like, our drawing sets are like 300, 400 pages, right? With like associated tables and things like that. And you've got like a binder of like 8.5 by 11 sheets like this thick that has all of this data as well, where the drawings say refer to table. Okay, so we're through the rationalization of the thing. So let's talk about detail. I love this quotation. I mean, it's been used a million different times, but it is my everyday. It's what I live and breathe, because all we do is look at like one-to-one every day. Like we have bolts in our studio, we have hex head, you name it, different kinds of screws. We're even talking about creating a new type of bolt for this project that we're looking at having machine custom for this, because we don't want to have exposed fasteners in certain areas, right? So the engineer said to us, you know what? You guys do this really well. You should create and design this bolt and patent it and then make a boatload of money off of it. It'd be amazing. So we thought, well, yeah, so we're looking into that as well. So our, our engineer we work with, David Moses, basically, with all due credit, he's awesome. He's a great guy, and they do really good work. But, this sentence couldn't be truer. The problem with typical details is the fact that they're typical. So when you're dealing with something that has hundreds of unique connections, these don't suffice. So what they actually serve as is a series of limitations. They end up being graphical representations of what the limits are. So, for instance, we've got an angled piece of hollow tube with a custom cast end member here that's got a pin driven through it, with a custom cut plate that's welded to a top plate that's bolted to another plate that's on a series of other custom plates that are then sitting on top of another plate bolted to a slab, right? Well, that angle that member comes in has a limitation. If it gets too shallow, it's not supporting anything. If it gets too steep, then it could twist the thing and we could be having problems and issues where we just rip the thing apart. So what these drawings serve as are a basis by which, or a set of rules rather, that we define how we approach every detail that we design, right? So, again, going back to this kind of drawing blown up a little bit here, is that, okay, so I'm basically, the reason this is included is because I'm showing all of these points that we have potential connections. So we have a potential connection where a purlin hits a primary. We have a connection where there's a plate on HSS. We have a connection where a prop comes into a plate where there's a splice. We have a connection detail where there's a plate going into concrete. We have another connection detail where there's a cross-bracing rod coming through the plate, right? We have another connection at the base where we've got bolts cast in concrete. To give you a sense of scale of this thing, which looks absolutely minuscule in this drawing, this thing is 1 meter deep plate by 750 wide by 1.1 meters high. And this is all custom fabricated steel. So they put this thing down, and get this, they've got to basically cast in 6 bolts, so 3 bolts on either side of this thing, and they've got to basically lift this like 700-pound thing of steel over these bolts and hope to hell that they align when they drop that plate down into the holes, right? So all those holes have got to be oversized in order to accept that. It's a hell of a task. So, what we do is we go through every single bay, every single connection, and we say, all right, is it meeting the minimum requirements? Well, what happens here is that every single time we have a primary here, there's a work point established. So what happens is the structural engineer designs this thing based on the work point, which is essentially the center line of all of the forces. They always have to pass through one point in order to achieve equilibrium, because otherwise, if you're off the work point, you're actually creating like a rotational force, which actually then creates a moment, right? Which will effectively, potentially tear the thing apart. But obviously, there are limitations to which you can be off the work point. Now, it's our job to basically understand and design all of these and understand how far, if we have to be off the work point, what are the limitations? And then usually what that means is that it's boom, poof, we've just created more work for ourselves because there's another problem we need to solve. But unfortunately, sometimes when you'll see I have a rendering of how much steel is actually packed into this. It's actually kind of ironic that the wood structure is mostly composed of wood, but it's jammed with so much steel at all of these points that it's almost like the antithesis of what the thing is trying to show. So it's actually quite entertaining when you see the drawing. You kind of laugh a little bit and chuckle and think, haha, right, wood, whatever. So from this, you can get a sense of the scale of this thing here by 250 wide, which is actually not that wide, right? Just, 10 inches, I guess? By what is that, I guess, 750 roughly, or 700 or something like that, edge to edge. So, not that bad, but, all of our drawings also have to indicate the welds too, right? We're not just doing design drawings, we're doing, assembly. So, again, we're showing our welds here in our different angles, and this is obviously showing the concrete here. You're seeing the cast-in bolts. Now, what's interesting here is to kind of save ourselves some time and get things kind of set up for us and prepped, what we're doing is we're working with the GC to say, you know what, let's simplify this a little bit. You guys are going to be pouring concrete way earlier than we're going to have our stuff fabbed in on site. So why don't we design a connection so that we have a plate, with cast-in tabs or rods that are embedded. And then what we'll do is we'll fab this connection here. So basically, this piece of HSS and this back plate here and this plate cast into the slab will already be there to receive our material when we go ahead and bring our plate and our members to site. So that basically what we can do is do a survey prior to the erection, have all the stuff ready and prepped for us so that we can basically just show up and boom, connect, right? And that's why the majority of the time you'll see the bolted connections as opposed to welding, because welding is much more expensive than doing a bolted connection. So here's a view looking at the underside, so looking at grade. You would never really actually see this in reality because you're basically standing inside concrete right now. But what this illustrates here is a bunch of, you'll see a bunch of these things tied into vertical face of concrete that I was just describing. And then here we see our deep purlins with our connections here and our rods going through, our tension rods over here and our trees over there. This is just looking at the top view of the thing, so you can see the thing from above. And so now what we're doing here is we're looking at a drawing of the thing in plan where we've removed some of the purlins because this drawing is so bulky that you literally almost cannot pan the file, like just pan in the viewport with all of the purlins on. And we're talking, like dual 6-core machines with some even 64 gig of RAM, and it's basically a challenge with some of these things. So, like $4,000 graphics cards. So it's very, very, very intense. And so what we're showing here is basically from this point over in this bay, we get 4 branches per tree. In the center, because the members are so much larger in the span and the arc is so much longer, we have to go to 6 branches in order to sustain all of the loads, right? And snow loading is obviously a huge component of that. So here we're showing, I've done a rendering of the connection essentially that we were just looking at in a drawing. Now this drawing I've included, and what I've done, it's actually a little bit difficult to read, but if you look at the black lines, Essentially, what they are showing is the outer face or edge of the wood, right? Because the wood is solid, you can't really get a sense of what's going on inside the wood. Remember I said the wood is basically packed full of steel. Well, this is a problem. We can't have, and this is like us optimizing things so that the rods, don't basically cut right through each other. But if you think of this rationally, if you've got to cut and bore and drill and mill that material out of the wood, what's left of it when you're done? Nothing. What are the chances that that bit is going to go straight through that wood on a compound angle on all three axes? Probably zero. So what that means is that all of this steel in reality is actually going to be just hammering into one another. You'll never be able to slide that thing through on site when you're having a crane hold up a half-ton or a ton, 2-ton piece of wood. There's not a chance in hell that you're actually going to clear that. So these are the sorts of things and the issues that we find when we do our work. And again, here you can see, what I've done is I've actually drastically reduced the number of components that are being shown here, but we call these things fly swatters, when really we could be using, there's a connection by a structural engineer, Bircha, that actually is a much more efficient means of actually doing what we're trying to achieve here. But what we've got here is, again, this is one of those splice locations, right, where it's packed full of steel. What's not being shown here is all of the rod that comes through here as well that conflicts with all of these plates here and everything like that. So there's a huge amount of stuff that I've reduced, but I'm showing here, you can see basically just a transparent material for the wood, and you can see all of these elements that are either face-mounted or inside the wood. There's a serious amount of steel in this thing. So here again is just a rendering of the base where you've got the custom plates welded and whatnot. Again, this is looking from inside the face up all of the purlins, and you can see how it's really dense here, and when we get to the splice, that's when we start reducing the number of purlins to the front edge of the veil, which is what allows us to kind of save a lot of money and installation as well. So that aside, now we have parametric constraints. Now, I absolutely, again, love this quotation because the part highlighted in yellow is what we do every day, which is crafting the timepiece and the machinery. That's what I love so much about this. Originally I started out, and when I graduated, I thought, I want to do the concept. No, the concept is the coolest thing on the planet. That's what I love to do. It's the overarching thing. It's what gets all the glory. But after working in firms for whatever, I guess 10 or 15 years, wow, I don't know if it's that long, but that seems like a long time. I basically thought to myself, well, no, actually, you know what? What is really the coolest part is the timepiece. To always work on the timepiece is amazing. It's a lot of fun to craft that and understand how that actually works. So a lot of you will recognize what this is, right? We've got a grasshopper graph, and we've got rhino geometry here, which is, like I said before, great at a conceptual level, works awesome. But when it comes time to, resolving the thing, the parametric of the situation is a little bit different than the parametric of the situation during the design phase. So what we're doing, and what you can see here is these highlighted cyane type members here. These are all elements that are considered to be similar. So what I'm doing is I'm highlighting, I'm saying all of these members that are being shown in this color are similar in the sense that their constraints and what they're linked to are all relatively the same. So they all are defined by the same parameters, which means that, I can use that one condition, 30 or 40 times instead of doing 30 or 40 unique modeling situations. So what happens is if we slide this plate up and down on the wood, then the arm moves with the plate, and also the trajectory of the thing through the pin actually changes as well. So we're talking about parametrics in a different sense now. We're not talking about it in a design concept, we're talking about it in a basically almost emulating what happens force-wise on the building itself. So what I've done is I've actually included a couple of slides here which illustrate this plate situation here. Now, what's awesome about all of this and why we use SolidWorks and CATIA and not Rhino or Revit is because that is a 1/4-inch piece of plate. It's a piece of plate. It's not a piece of geometry that looks like plate. It's plate. It has mass, it has characteristics, it has finish properties. These are all things that we can schedule and put into a package of drawings for a fabricator who only understands that language. So really our drawings are way more, have way more information than BIM could ever conceive of thinking of offering to us at that level, right? So what happens here is that, for instance, we change the angle of the primary. Well, automatically we choose what the relationship is and which plates we consider to be locked in size and which plates can extend. And in this case, it's the plates that are adjoined to the plate mounted on the vertical surface, not the assembly on the HSS. Because if you think about this from a manufacturing perspective, we want to be able to control the length of the HSS, right? Because the material for that is more expensive than a piece of plate that's just cut, right? So anyhow, what we have here again is we're just showing that series of connections here relative to the face. And again, you're seeing these highlighted blue members, which are all essentially have the same characteristics or properties. Okay, so the last component, I hope I'm not, maybe I'm close here to finishing. So the last component is the tools. And when I say the tools, I don't mean the tools that we use to draw, I mean the physical tools that are used to make these things. Now, because I'm going to talk primarily about wood, I'm not really going to get into steel because we don't really have much time. I could spend 3 hours talking about this project if I wanted to. But what I'm basically going to talk about here is that, you know, these are basically, they're end mills, right? But they're, I mean, drill bits for all intents and purposes, let's say. They're just very sophisticated drill bits. And I'm basically just showing a very, very small fraction of what is possible. But you're seeing essentially what happens when a wood or when a bit passes through wooden material, right? That's just basically the principle of this, is that these are kind of the tools and things that we have available to us. And this slide is essentially, the reason I included this was part of an email that was like 7 pages long that we got from the wood fabricator, Structurlam in Penticton that I visited, 2 weeks ago. And basically what the guy did was he sent me an email that basically said what the restrictions were of the tools that they had. Now, why would he send me that? I mean, why do I care? Well, I care because my drawings and my geometry is going to prep and mill my model to receive or allow his machine to process the material. So what I give him will be basically, he can push the button on the machine and the machine will actually mill what I have specified by 3D points on a surface. So I'm going to pre-mill everything for him. Now, having said that, that's great, but when we're talking about an organic material like wood, there's always this facet of a guy standing there cleaning the surface because the machine can only do so much, and then it still comes down to a guy standing there and a person inspecting every single element of that surface to make sure that it is acceptable. So here's what I'm talking about. In our primaries, you know, we've got an end mill that needs to come down, plunge the wood, and cut across. But that end mill is going to leave a radius on the end because it's round, right? You don't draw a square cut edge there, right? But you do draw a square cut edge here because it's a saw blade that's going to plunge the wood, move across it, and pull up. Therefore, you get an arc, the diameter of the blade, right? So what we're doing is our geometry is way more sophisticated and actually is taking into account the actual tool that is going to process it. I'm sorry, I get excited about this sort of thing because it just blows my mind. I absolutely love this stuff. Like, I mean, it's just, you know, it's like my Tonka truck. It's awesome. So seeing this thing, and what's even better is you see this thing and you think, my God, that's impressive that that machine can do that, right? So then we have our prefab piece of steel here that just literally will just slot right in to that. And you know, what's fantastic about this is that we have a guy in Ontario that makes the steel, is going to ship a whole bunch of, mock-up parts out to BC, and they're going to just dry fit these things in and, you know, modify and tweak the machine here and there in order to actually just take the plate, so that when it gets to site, we just crane in our piece of wood and just sit it down on our steel and then insert our bolts, and we're done. And so what you can see here, is these bores right through the material are basically going to receive a pin. And so what's interesting about that last slide I showed you with the limitations of the tool is that this hole actually has to be undersized, because it's got to receive a stainless steel pin that has to be hammered through the wood so that the actual pin is larger than the wood, so that the friction of it inserted in the wood is actually what holds it in place after the fact, which is kind of a scary concept when you think about it, but it's so tight that there's no chance in hell it's ever coming out. So what we have here is just some samples of all of this stuff has been either laser, plasma, or water jet. The steel has been processed. And you can see that I always love seeing this, because these are our part numbers, right, drawn on steel. And I think, yay, that's the fruit of our labor, right? These things have been cut. They're showing our part numbers. They're showing how many pieces, right, based on a table that we have basically created. And then this is after they've been post-processed, and they've been through paint, through weld. They've been sanded, refined. That's kind of what some of those HSS members with the plates look like. So I'm kind of running out of time here, so I'll speed up a little bit. But basically, you know, when we come back to, oh, hey, I lost a slide there, actually, I think. So I did have a slide before that. Yeah, I had a slide before that. But anyhow, there was a quotation from Wired magazine last December that basically said that in 10 years, 70% of jobs in the workplace will be replaced by machinery. Not here. This is the exception. What we're dealing with is, as I said before, everything is atypical. You still need people when you get that specific, because yes, the machines can do all this stuff, but someone needs to operate the machine. So maybe the percentage of manual labor required will be reduced, but you still need people, because there's an incredible amount of ingenuity and brain power, in human brain power, being employed on stuff like this. So this was just a simple table to show, yes, milling helps us save time and some money, but at the end of the day, when it comes to the finishing parts, finishing it all off, there's still a huge people component in that, and that shouldn't be underestimated or downplayed at all, because it is really important that those people are there to, help make these things happen. So I've got a video here. I think Miriam's just going to press play. All this is, as you can see, this is a Creno 5-axis CNC mill. What's happening here is this guy's got this 3-ply structure. This is actually an alternative to a structural concrete slab. They're actually using like a 3-ply prefab wood flooring system. And what he's doing is the mill has actually come down and it's cutting the wood on, well, in this case, a straight angle, but it cuts it at different angles and whatnot. And so there's an articulating arm in there, and you can see all those drill bits here on the backside. This is the machine basically comes to the end and says, I need this one now, grabs the tool it needs and comes over, does its work, puts it back, takes the next one, does it. Very similar to how we have here in the shop, but like 50 times more sophisticated and cooler. Sorry. It's really an amazing thing when you see this thing. Like, they've got gantries everywhere, right? Because you can't just get like a couple of guys to lift one of these things and put it on the bed, right? But this is the machine I was talking about, whereby, if you need a lineup for this machine, because it's $5 million, they've only got one. If there's a lineup, there's a wait, right? And that's money, and time. So anyhow, and here you can see basically just a giant prefabbed open web wood joist. Here, basically, what's really interesting about this environment is that because we're dealing with wood, right, and all these curvilinear members, and as I said before, they all have memory because it's an organic material, they have to actually humidify and control the humidity in the air. So what they have on these walls here are a series of tubes and pipes which actually disperse moisture into the air to keep the wood moist so that it's not drying out, because they've exposed all of these different areas with all of these end cuts and everything. It's really an amazing thing. It's beautiful. It's like poetry in motion. It's really amazing. So what we're showing here is I'm just basically showing the scale of a person relative to the size of this gantry. I mean, this is a facility essentially that we're going to be using to custom cut. And over here, what you're seeing is they're actually setting up a $15 million 5-axis CNC machine here. It's a German, I forget the name of the unit. But anyhow, basically you can see they've got railroad tracks on the floor here. So what this thing can do is can actually move the material up and down or move itself up and down and just basically go inside and cut all around. It's just unbelievable. I mean, this thing is the coolest toy I've ever seen in my life. But it's really amazing. So basically, to go back to that whole thing, because this is my second last slide, is that this guy still needs to be there. You can't trust this thing to just do what it does. Someone needs to be there standing, watching that thing, and making sure that what we have now done, right, and what the machine is processing, and what he is ultimately going to, give us as a result, all of that needs to exist in order to have this as a successful process, make it a successful process, and make sense, right? Financially, everything. And so I end with this, which is to say that when I mean architects, engineers, everybody who is involved with this process. That is what we do. We craft, exquisite timepieces which happen to be architecture. And it should not be treated as anything less, because everything should be it should be your obsession. And that's why I finish with that, because that is what our obsession is. So that's all I have for today.